Hello everyone, thanks for joining the virtual presentation. My name is Lu Zhang. I'm from University of Alberta. Today I would like to talk about model predictive controller design for pulp digester. This work is done with my advisor, Professor Steven Dubjavish. The outline of my talk today is, first, I will introduce the background behind this work. Then I will dive into the modeling for a pulp digester. In addition, based on the model discretization, the model predictive controller is proposed. In the end, we give a numerical simulation to evaluate our design and conclude our results. The pulp and paper industry plays a very important role in the world, especially under the pandemic situation of COVID-19. The demand for various paper-based products are increasing, such as the personal hygiene products, the food packaging products, and the paper-based medicinal materials. More than half of the globally produced pulp comes from the craft pulping processes. Among these, the most critical piece of equipment is the digester. As shown in this figure, the wood chips from the chip storage are cooked and washed continuously in the digester before the further refinement in the mill and paper operations. Basically, most of the continuous digester contains three basic zones: an impregnation zone, a cook zone, and a wash zone. Most of the delignification reaction occurs in the cook zone, where provides high temperature for the reaction. In order to describe the complex delignification process, there are three typical models proposed. One of the widely used is Matroson's model, which is a set of partial differential equations derived by the mass, momentum, and energy balance equations. In this model, as shown in this figure, each volume in the digester contains three phases, namely solid phase, entrapped liquor phase, and free liquor phase. In the past decades, considerable efforts have been expended to model the process and design the controllers. However, there are still some challenges. In most of the contributions, the PDE are approximated into large scale of ordinary differential equations. It's difficult to capture the spatial dynamics within the digester. In addition, the system is non-spectrum, and therefore other arguments of the low-dimensional representation by having just a few eigenmodes to describe dynamics do not hold. On the other hand, for the operation of advanced industrial processes, we are facing with some difficulties as well, like there are some physical limitations of sensors and actuators. So in order to realize good control and monitoring, we use Kali-testing time discretization approach to realize model discretization without model reduction. Then the MPC is proposed to achieve desired performance respect to some system constraints. Since the main delignification reaction occurs in the cook zone, we select this zone as our study objective. Based on the model proposed by Matroson, the following assumptions are considered to obtain the simplified model. Hence, from control and monitoring point of view, the following variables are considered as the state of the model. Therefore, the mathematical model is described by the following 5 nonlinear PDEs. The boundary condition and initial conditions are given in equation 2 and 3 respectively. The 5 states are coupled together by the reaction rate RS and the mass diffusion rate DEA, which have the following expressions here. Since this model is 5 coupled nonlinear hyperbolic PDEs, which are almost impossible to solve directly, we do the model linearization around the steady state to describe the process local dynamics. Here, we simply take temporal derivative term as 0, then we get the steady state equations as shown in equation 4. After do the state transformation, we obtain the linearized infinite dimensional model as shown in equation 5. The corresponding boundary conditions are shown in equation 6. The specific expression of operator A is shown in this slide. Here the VZ, find Z are spatial functions, which are related to the transport speed and the nonlinear term evaluated at the steady state. In addition, we consider a bounded control operator B and the unbounded observation C, which are given here. Since MPC is designed in the discrete time setting, we need to consider the model discretization. Instead of using the standard PDE model discretization approaches, such as POD and FDM, we use Kelly testing time discretization framework because it preserves some important model properties like the energy, stability, controllability, and observability, which are important to the controller design. Then I will introduce the Kelly testing time discretization approach briefly. Let us recall the linearized infinite-dimensional model, shown in equation 9. For a given time discretization interval h, the Kelly testing discretization is given by equation 10. Here we approximate the time differential by backward indifference. On the right-hand side, we average between the present and past state, both in the state and output equations. After some basic calculations, we have the infinite-dimensional discrete time state space model as shown in equation 11, where AD, BD, CD, DD here are the discrete time spatial operators and have the expressions as shown in equation 12. Here the common terms are referred as the resolvent operator. Once we have it, we can straightforward get the discrete time spatial operators. The resolvent operator can be obtained by utilizing the Laplace transformation. By solving the equation 13, we have the solution in frequency domain. Further, we can get the resolvent operator here, which mapping from the initial state to the state solution. Therefore, we can get the AD, BD, CD, DD operators directly. Then, based on the discrete time state space model, the MPC can be designed and implemented. This is a typical infinite horizon open loop objective function, which can be further cascaded into a finite horizon problem by assuming the input is 0 beyond some horizon and adding a penalty term for the output. Here is a finite horizon open loop objective function subject to the system model and the input-output constraints. Here we have the penalty term in inner product term form to realize the stabilization. Q bar here is a spatial operator to penalize the terminal states, which is a positive solution of the discrete Lyapunov equation, or equivalently the continuous Lyapunov equation. This is one of the properties of the Kelly testing transformation. Then the objective function can be written in the quadratic form as shown in equation 18. Similarly, the original system constraints can be written in the linear inequality form as shown in equation 18. Based on this quadratic programming problem, we can implement the algorithm to our digester model. The following model parameters and the MPC parameters are considered. As shown in this slide, the open loop states converge to their corresponding steady state rapidly, which indicates the original plant is stable. However, in practice, there exists some unknown disturbance which makes the open loop system potentially unstable. So, in this slide, we consider the distributed disturbance in the system. We can see there are some oscillations in each state profiles. In order to stabilize such disturbed system and satisfy some input and output constraints, the MPC is implemented. In this slide, we can see clearly from the following perturbations of the closed-loop state profiles under the MPC law. The closed-loop system is stabilized because all of the states go to 0 with a fast converge rate. This can also be verified from the output profiles shown in Figure A. The open-loop output response is oscillated due to the distributed disturbance. The MPC controller is able to realize disturbance rejection and satisfy the given constraints. The corresponding manipulated input is given in Figure B. In summary, in this work, a continuous pulp digester was approximated by a discrete time system, utilizing the Kelly testing temp discretization without model reduction. The MPC controller was designed to the continuous pulp digester, which is modeled by a set of nonlinear coupled hyperbolic PDE. The proposed MPC is capable to steering the original dynamics to the steady states without validating the physical constraints and make a good performance in the presence of the disturbance. Thanks for listening.